So we're going to begin by doing the moment of inertia of a rod. We're going to start by doing it around its center, then we're going to do it around an endpoint. So when we break apart a rod, we're going to assume to start with that it's around its center. And what's going to happen is we're going to break the rod into little pieces. The formula we're going to actually use is the calculus formula. I is the integral of r squared dm, okay? And we're going to break it into little pieces. So this piece, this piece, this piece. So what's going to happen now is we are going to get each of the distances. So we're on the x-axis. So we're going to get, for example, like we'll add up this little infinitesimally small piece. Okay, it has a mass of dm. It has a position of x. Okay, in this case, our r is going to be our x. So it's going to be really x squared times dm. Now we have to write dm in terms of dx. How are we going to do that? Well, we're going to, in order to get a function for dm, what we're going to do is we're going to say, hey, we've got a linear density. Linear density means we're talking about the mass over the length, okay? The total mass of the entire thing divided by the total length. And then this is called the macroscopic version of this, and then we also have the microscopic version of this, all right? The microscopic version is going to be dm over dx. Okay, so now what we're going to do is we are going to say dm is actually equal to m over l times dx. So that will allow us to substitute in for dm. And so we're going to integrate x squared m over l dx. Okay. Now we're going to do this two different ways. Once we're going to, the first part, we're going to get the I around the center of mass. If we want to get the I around the center of mass, then we are going to integrate this thing, right? And I'm going to pull out the m over l. Okay, so m over l is going to come out here. We're going to integrate x squared dx, but we're going to integrate from negative L over 2 to L over 2 because our axis is right in the center. All right, so if you think about it, right, you're going to integrate from, if you put your axis right in the center, you're going to integrate from negative L over 2 to positive L over 2. Okay, this is negative L over 2, this is positive L over 2. So when I integrate that, I is m over L. The integral of x squared is x cubed over 3. And I'm going to go from negative L over 2 to positive L over 2. Now, the good news, something we can do is the fact that we can say, hey, you know what, it's symmetric on both sides. So you're going to just basically accumulate what you get on both sides. So what I can actually do is I can change this into double. I can say 2 times m over L, x cubed over 3, and then I'll integrate from 0 to L over 2, which will make the math a lot easier. So when I do this, I'm going to get 2m over L times L over 2 cubed divided by 3 minus 2m over L times 0 cubed over 3. So that's going to go to 0, and I'm going to get 2m over L, L cubed over 24, okay? And you get the 2 and this will 12 will cancel each other. The L and this will cancel each other. And I get 1/12 ml squared. Okay, now if I do the rod around its endpoint, I'm going to do the exact same thing, except I am going to integrate. So if I'm doing the I around its endpoint, we're going to do the exact same math. So I'm going to go back and actually pull the math that I have here. I'm going to have the integral of x squared m over l times x, the integral of x squared m over l times dx. But now I'm going to integrate from 0 to L because now what you've got is you've got a distance. So here I'm going from 0 to L. Okay, so when I do that, the only thing that's changing are the limits. So when I integrate this, I'm going to get m over L times x cubed over 3, and I'm going to go from 0 to L. So I get m over L times L cubed over 3 minus m over L times 0 cubed over 3, right? But that's all 0. So when I do this, I get 1/3 ml squared. So the rotational inertia of a rod around its endpoint is 1/3 ml squared, and the rotational inertia, so let's highlight that, the rotational inertia of a rod around its center is 1/12 ml squared. And we are done with that derivation.